Hello there. Welcome to our today's science lesson. The topic for the day being changing state of substances. In our previous lesson and lessons, we have talked so much about the three states of matter, that is solids, liquids, and gases. And we have seen in particular the properties or the characteristics of solids, the characteristics of liquids, and the characteristics of gases. We even went further to look at particular examples to ascertain or to confirm or to try to understand the properties that had already been mentioned about the three states of matter. And those examples were examples that we commonly interact with. In particular, what we did in our last lesson, we looked at the so many examples associated with the gases as a property or as a state in the three states of matter. But in that state, in those three states, gases in particular, going to their properties and how those properties can be changed with the change in particular conditions. So in today's lesson, we want to look at how one can change from one state to another, because you realize that in some cases, the three states of matter must always work together. In other cases, you have to transform one state to another for you to achieve whatever you want. Maybe it will be good to look at some rough areas where you find change from one state to another is helpful in one way or another, depending on what you as an individual you are after. Look at something like a refrigerator. You want to keep your items in a fridge at a particular temperature, which is obviously at a lower temperature. How do you achieve that? We only use the fridge, but so many of us don't know how a fridge works. You only see that body. But behind that body, inside at the back, there is a lot of work that was done, and inside those apparatus, those gadgets you will see at the back, we have what we call a fin. Something like that looks like this. Then with the metallic strips crossing by. So in these strips, which are tubular in make, we have a liquid that is always moving between liquid and gas through evaporation. And as it moves from liquid to gas, it loses some heat, which goes out through the fins, and at the end, it leaves the surface cold. So this is an application of change of state, where that change of state is helping us achieve cold conditions in a fridge. Another example is, for example, if you have an open point of selling kind of ice cream, an open point of selling ice cream, you find that that ice cream should be at a lower temperature. Otherwise, if you raise the temperature, the ice cream will melt, and maybe when you will be serving it in the amount you want as you are selling, you may not get exactly what is required. So you have to keep it at a cooler temperature so that it maintains that shape when it is put at whatever dispensing point. Now, how do you achieve this? And yet, maybe where you are, there is no power. You will carry with you solid carbon dioxide. Solid carbon dioxide. Solid carbon dioxide. This is the formula of carbon dioxide. Now, this solid carbon dioxide, when the temperature is raised, it changes from solid to gas directly. Changes from solid to gas directly. What we normally call dry ice. This is what we call dry ice, because when it is in solid state, it looks like ice which is in water, the normal ice water. They look alike. But when you heat this solid, or when temperatures are raised, that is the heat, or raise the temperature, you heat or raise the temperature, then it changes directly from solid to gas. The same as when you are talking about ice water, which is also solid, and when you heat or raise the temperature, it now goes to water. And here water, we are talking about a liquid. Here is a gas and this is a liquid. In either cases, there are advantages associated with it. There are uses associated with it. Like now this one, it makes the surface that was holding that dry ice to be cold. And that surface will be that ice cream. So as the dry ice goes away, it leaves the surface of the ice cream cold, maintaining that solid form of the ice cream, not in a molten or melted form. But now, in all these processes of changing state, there are names associated with it. There are other explanations associated with it. And those are the explanations and the examples and the names we are supposed to discuss in our today's lesson. That is in the changing of state of substances. Now we have to start off by reminding ourselves the models we had in our previous lessons about solid, liquids, and gases. You remember in that previous lesson, we had 3 models. And in these models, we talked about a solid, particles being very close by. Then we had liquid, particles being a little bit far away from each other, and gas, particles being far away from each other. Now, this is the same model we are going to use to do our further explanation and even use examples and give the names associated with the changes in state. Now, if you start off with a solid and you are supposed to move from a solid to a liquid, you have first of all to look at the particles that are in that model, the particles that are in that substance, and what is happening to those particles. So these particles in a solid state will be closely packed together, vibrating in a fixed position. Vibrate in fixed position. Those are particles in solid state, vibrate in fixed position. However, if you are to move from a solid to a liquid, then the particles will have to be done something, and that is heat energy is introduced. Heat energy is introduced, and this heat energy will make the temperature to go up. As it goes up, the particles will absorb. They will absorb the heat energy. These particles will absorb heat energy. In doing so, their vibration, which is in a fixed position, will be more vigorous. The vibration will be higher. So, as they break in a much more stronger way, they break off from each other. The high vibration makes the particles to break off from each other. As they break off, moving a little bit far away from one another, they now become a little bit more free to move in what we call particles start rolling over each other. So because the particles are now more free, they start rolling over each other. As they roll over each other, it means the product that will be formed, which is now a melt. A liquid is just a melt of a solid. So the product that will be formed because of what has happened on this solid here, which is a melt, having the particles now rolling over each other, the liquid flows. The liquid now flows. To confirm that the particles are rolling over each other. So we need to know what is this process of changing from, how do we call that process of changing from solid to liquid? And the process is called melting. This is a process called melting. And how do you achieve melting? Melting is achieved by heating the particles in solid. They start vibrating much strongly, and by vibrating much strongly, the particles break off from each other. By breaking off from each other, they start rolling over each other. And by rolling over each other, what your eye and my eye will pick out that whatever you did has been achieved is now the liquid will start flowing. If you pour off, it will be poured, meaning that it is flowing, to confirm that truly the particles are flowing over, rolling over each other. The process being melting. So this is the process. Now we also need to realize that each substance has its own melting point. Each substance has its own melting point. So which means you cannot pick the melting point of, for example, this substance to be the same as the melting point of maybe candle wax. Being that the two substances are different, they have different properties, even if they are all solids, then each one of them will have its own melting point. Maybe to pick out one of the substances that is common, let's talk about, for example, water and mercury. Water and mercury, these are common liquids that I'm sure you have interacted with. Mercury is a liquid you will interact with when you are talking about a thermometer. And the water, that is a kind of life. Water is just life. You are always with the water. So looking at water and mercury, the melting point of mercury, is negative 39 degrees centigrade, and the melting point of water okay, we can talk of water ice. Water ice, because we also know the dry ice. There are two types of ice. We have the dry ice, that is CO2, carbon dioxide. Then we have water, but we are talking about in particular ice. This one is at 0 degrees centigrade. But remember, when we are quoting these temperatures, you have to make sure that you are talking about at sea level. Why this? We have to mention the sea level because as you move above the sea level or below the sea level, pressure changes. These are areas of different pressure zones. Therefore, they will have to exert different levels of pressure to that mercury or to that water, depending on where you are. So at sea level is when you talk about negative 39 degrees centigrade or 0 degrees centigrade. But anywhere above this sea level, then you will find that the melting point of mercury or the melting point of water will automatically change. But we have to go with the standard ones, which is at sea level. Something we also need to note is at one point you may want to try this, maybe at home. Probably you are at the coast and you want to try this. Then you wonder, if I have a thermometer, this thermometer is not giving me 0 degrees centigrade at which this water of mine is melting. Then what is it that is different from what I've just learned. You have to realize that, one, sea level will affect, but two, we also have what we call impurities. We also have what we call impurities. You must be having mercury or water that is free of impurities. Not just looking at sea level, but also free from impurities. What does this one mean? It means that if you have an impurity, in any of the substance, remember we are talking about substances, in any of the substance you are working with, then the impurity will lower the melting point. Even if you are talking about at sea level, but the melting point will have to be lowered. Here, I mean, if for example this water was not a clean water, pure water, you have frozen it, it is now ice. You want to do the process called melting. So you start warming up that water ice with your thermometer. Then you discover that just before you reach 0 degrees centigrade, if the water was not pure, then the water will start melting. So I've stated one thing, impurities lower the melting point of a substance. The other thing you have to note about impurities also, the melting point will not be sharp. That is, it will not be particular temperature like we can give out 0 degrees centigrade and no any other range. But if the water is not pure, that is, if the substance is not pure, then we shall talk about a range. You can talk of, for example, if it is water, you can say the melting temperature was from -5 degrees centigrade to, let's say, -1 degrees centigrade. Looking at the temperature, this temperature is less than or lower than 0 degrees centigrade. That's one. Two, again, it is working at a range. You don't have to operate in a range, -5 to -1 degrees centigrade. Now, I don't mean that when you go to try with the impurities, this is the temperature you will get. No. Remember, you also have to look at the type of impurity. You don't expect an impurity of sugar to give the same effect as an impurity of maybe common table salt or an impurity of particles of sand. They will obviously affect in their own different ways. But what we know, or what we need to know, is presence of impurities lowers the melting temperature of any particular substance. Now let's look at the next part, moving from a liquid to a gas. Moving from a liquid to a gas. So the same thing must be done, that is, we have to inject in heat energy. As you inject in heat energy, the particles, just like the solids did, the particles of the liquid will also do the same, that is, absorb the heat energy. On doing so, the rolling over process becomes faster. The rolling over process becomes faster. As it is faster, it reaches a point whereby the particle that was rolling now doesn't just roll, but it breaks off completely. It's like a particle that is being thrown off a cliff. Imagine of a high point, like a cliff. Then, probably maybe there is you have seen it like in Olympics, there is this sport where people jump from a cliff deep into a point of deep water. Now, if you are to jump to a far point, then it means you will have to move very fast from this point. But when you are starting off, you will start off by moving slowly, slow movement. But as you proceed, you reach somewhere here, you will be a bit faster. We can relate this to this state of matter, that this slow, we can relate it to solid. But as you gain more momentum, as you are moving faster here, you can talk about a liquid. But on reaching at this point, you will not continue with this surface. Instead, you will be now in airborne. You will be airborne. Being airborne, we can assume you as a particle, you have now broken loose from this particular point. So at this point, when you are airborne as an individual, probably you are the one jumping off the cliff, heading to this deep point of water as a spot. So at this point, we can say now you are a gas, free. Even if you are so many here, you are not in touch with any other. You are the only one airborne. So we can say at this point, you are a gas. So what are we seeing? When you are at this point, the speed at which you will be moving is much faster than this one. And this one is faster than this. Why? Because of the addition of the more energy, the momentum you are gaining. So if there are these particles, we can talk about the heat energy. So here the particle breaks loose from each other, and therefore you can call it a gas. We need now to know which process is this. The process of moving from a liquid to a gas is called evaporation. The process is called evaporation, vaporizing. You can also say vaporization. Vaporization. Now, there is some slight confusion to some between boiling and vaporization. I've just said the state of changing from a liquid to a gas is vaporization. But we always associate vaporization with the boiling point. Then what is the difference between vaporization and boiling point? Vaporization is just that state of changing from a liquid to a gas, which can take place at any temperature. It can take place at any temperature. But when you talk about boiling point of a substance, let's be in particular, when you are talking about water, we know very well that the boiling point of water is 100 degrees centigrade at sea level. 100 degrees centigrade at sea level. Does it mean that evaporation or vaporization only takes place at 100 degrees centigrade? Obviously not. When you have just spread your clothing after washing on a clothesline for it to dry, you will find that even before achieving the 100 degrees centigrade, the cloth will obviously dry. But they are having water in them, not another liquid, water. But this water is being lost at a temperature less than 100 degrees centigrade. Then what is it that is happening? Whatever is happening is evaporation or vaporization is taking place. Just a mere change of liquid, which is in the clothing, to vapor, which is moisture into the air that you will not be getting. But that is being done at a lesser temperature than 100 degrees centigrade. But when you talk about boiling, this is the temperature at which, the highest temperature at which a water molecule will move from liquid state to gaseous state. So this is the very maximum temperature at which any water molecule can be changed from liquid to gas. Or the other way around, we can say it is the least temperature. The least temperature a gas can be changed to a liquid. The least temperature a gas can be changed to a liquid. That is obviously the process called condensation. 100 degrees centigrade. So there is a difference between evaporation and boiling point. Now that is one way, changing from solid to liquid and liquid to gas. How about the reverse process? Because we also have that process of losing energy and not gaining energy. So when you're losing energy, losing heat energy, we also have doing the same, losing heat energy. So what do we have? Starting with the gas, when losing heat energy, the particles here, which are in gas form, we are talking about gaseous, though water, but in a gaseous state. When you lose heat energy, the particles reduce their speed of movement. And on reducing their speed of movement, they come closer to each other to the extent that they make an attraction force between the particles. On doing so, they now appear to be at a constant point. In gas form, you cannot even realize it is there. But in liquid form, now you will realize, here I have a liquid. It's good maybe we use an example that is real for us to get this. When you wake up early in the morning, you find dew, maybe on grass or any substance that's around cobwebs. You will find a liquid on that cobweb. You will find a liquid on the leaves of the grass or plants. Where does that liquid come from? How was it formed? It came from air. Air that was carrying water vapor. Water vapor that is a gas. But since at night, temperatures sometimes go as low as 0 degrees centigrade or even lower, then the temperature, so long as is achieved to make sure that the temperature that you have at night cannot sustain water in gas form, then it makes the particles of water in air to lose heat such that they reduce on their rate of movement to clamp together, attract each other, moving themselves from a gas to a liquid. That process is what we call condensation. Condensation. That process is what we call condensation, the process of moving from a gas to a liquid by gaseous particles losing heat energy, being very slow in motion until now they form a liquid. A further process can also be done if you can reduce the heat energy much more than what you did earlier. Then this liquid water will now turn to solid water, what we call ice. That process is what we call freezing or solidification. Solidification. But the best term to go for is freezing. So freezing is the process of turning a liquid into a solid by losing or reducing heat energy in the particle. How do you lose energy or reduce the heat energy? It is done by what we call cooling. Cooling. So even this one is cooling. So in the process of cooling, you achieve condensation. In further cooling, you achieve freezing. But you also need to realize that not all substances undergo this process. There are those that will still undergo the same, but there are those that will undergo a different process. So we also need to look at such. This one, the best example you can use here is water. That's the best example you can use here. But the next process I want us to discuss is that process of moving from solid direct to gas. You move directly from solid which is close by to gas which is far from each other. Now, this is a unique process such that you don't go through a liquid state directly from solid to gas, just because heat energy has been added, heating has been done, or the reverse also happens. You can move directly from a gas to a solid just because you have done some cooling. So which type of process is this, whereby you move directly from solid to gas? This one is called sublimation. So sublimation is the process that a substance goes through by turning directly from a solid to a gas without going through a liquid state. Most of the substances that have this process, that undergo this process, require very little amount of heat energy, to change from solid to gas. We say that they exist in molecular form, something that we shall discuss in more details later on in our science classes. So they only require a small amount of heat energy and they turn directly from solid to gas. The same from gas to solid when cooling is done. In terms of particle energies is the same. In solid state, the particles are close by, they vibrate in fixed position, but in gas form, they are far away, they have broken loose from each other. A good example of such is dry ice. So here we talked about water, ice, and here we are talking about dry ice. We also have iodine crystals, ammonium chloride. There are so many that we can use as examples to give this explanation of sublimation. Now, something else we need to note, whether you are talking about sublimation or this other process where solid, liquid, then liquid to gas and vice versa, that when a substance changes from one state to another, there is no loss of material. There is one who can imagine, maybe if you have a cube of water, this size, then on melting, you have maybe a cup that is holding the liquid and it reaches maybe to that level. There is one who can try to imagine that this one is bigger than this or this one is bigger than this. And in most cases, people will imagine this one is bigger than this because ice, on forming ice, it becomes a bit bigger than liquid, especially if you will be talking about 4 degrees centigrade. The liquid may appear to be of smaller volume than that of the size of the ice cube you are talking about or you are dealing with. That one is not true. The volume here and the volume here is the same. The number of particles here of water and the number of particles of water here are the same. And the same too, even if you have a very big box or container holding now steam, which is coming from this small cube of water, these and these are all the same. They are all the same because you haven't added any molecule, neither have you lost any of that particular substance. Something else you also need to know is during the change of state, particles or a part of that substance that is on the outside, changes state earlier than those that are inside. So, if this is ice water, then we expect the particles that are on the surface here to first of all change state in the process called melting to form liquid water, and not the one that is at the center and not the one that is at the center. Reason being, the ones that are on the surface will easily gain the heat energy, making them vibrate even stronger, much earlier than the center ones, and when vibrating, breaking off to start rolling over, making it to melt. So we don't expect the inner part of the cube to melt first before the outer part. The same to this water. If you heat this water, then we expect the ones on top to start evaporating early before the inner ones. And that's why before water starts boiling, you will start seeing steam. Steam is not a gas as such. It is still a liquid, but a liquid that is having more energy. And as it continues gaining more energy, now it changes to a better gas, and that's why you will never see it, because the particles will have moved far away. But if the conditions will not be favorable enough for the steam particles to break away from each other, then you will find it is forming a dense fog. It will form a dense fog, meaning that the particles have not found a favorable condition to break far away from each other to be comfortably called a gas. And instead, it now forms fog. So, as you do that, those on the surface will break off early in the process called evaporation before the ones inside. Further information that we need to note about now evaporation and boiling. Remember, I said that it is a point of confusion to some, the difference between evaporation and boiling. I will wish we go a little bit deeper into that. So we look at evaporation versus boiling. Evaporation versus boiling. Evaporation is the process of a liquid. This is a liquid changing into gas. Just that process of a liquid changing into gas due to a heating process. If you are heating, then the particles in the liquid will gain more heat energy, making them change into a gas. The process takes place at any temperature. The process takes place at any temperature. Even if you know water boils at 100 degrees centigrade, but evaporation can take place at any temperature. To confirm that, if you can be asked that can you substantiate your explanation, or you are claiming that evaporation is different from boiling, then you can use an example of, for example, clothing on a line. During the day, temperatures can be as high as maybe 25, 27, 29, 31 degrees centigrade. Just that. But you will find at the end of the day, the clothes will be dry. But was it at 100 degrees centigrade? No. What happened? The water that was in the cloth had to evaporate. So that's just a confirmation that evaporation takes place at any temperature, and it's just the process of changing from a liquid to a gas. But on the other side, boiling is the point at which the liquid will change from liquid state to gas state, and no any other temperature above that temperature can be sustained by the same liquid. So I mean, it is the highest temperature at which a liquid changes from liquid state to gas state. Alternatively, you can say it is the lowest temperature at which a gas can change from a gas to a liquid in the process called condensation. They mean the same. The highest temperature at which a liquid can turn from a liquid to a gas during the process of heating to cause evaporation. Or it is the lowest temperature at which a gas can turn to a liquid in the process called condensation. That is boiling. Now, to show that boiling is different from evaporation, during heating of a liquid, let's use a little bit more of this. You are heating a liquid. This is a liquid, and this liquid is undergoing this steam, which is just part of a liquid but almost turning into a gas. So being in gas form, it is up there. Before boiling, you will see this, and this steam will be seen maybe on the lower part of near the surface of water. But as you move far away, then it is no longer as close as that. It will now be far apart, and that's why it will be clear. That is unseeable. You cannot be able to see it. Unseeable. But this one, steam, you can see it. But this one, you cannot see it. Why? The steam particles or molecules will have gained more heat energy. Remember, the environment is also hot. More heat energy for these particles now to move far away from each other, until now they are single in nature, not able to be seen. That is evaporation. For boiling, you will find that before the process of boiling, and I will wish you go try it at home. Look at the water as you continue heating. You will find that the first thing you will see is some steam to go out. Then you will start seeing small air bubbles coming out of the water. And they will start from the bottom as they proceed upwards. Then after some time, the air bubbles will stop being produced. On stopping, then you will start seeing bigger bubbles coming out of the boiling container from the bottom, not the top, from the bottom as they go up. Now, what does all this mean? The first part I've already explained. This steam, which when moving higher, it will gain more heat energy, then move far away from each other until you are not able to see it. Two, we have these small air bubbles. This is just that gas. Particularly, we can talk about oxygen gas that was dissolved in the water. That's what they always say, when you boil water, you expel all the gases that were held in the water. When you talk about fish using oxygen in water, where do we get that oxygen? This is the oxygen that has been dissolved in water. So on boiling, you expel that type of gas, oxygen, and so many other gases that can dissolve in water. When you boil, you expel those gases. So in the process of being expelled, they go out as small air bubbles. When you find that the air bubbles have now died off, they are not being seen, it means all the gases that were in the water have now been fully expelled. all the gases that were held in water, that is dissolved in water, have now been fully expelled. So that is a water gas-free or air-free water. After that, you will now start seeing bigger bubbles of air which move from the bottom to the top. These bigger bubbles are not because of another gas that has been maybe created. No. A gas that is like oxygen. No. This will be a gas, but now from the boiling liquid. A gas, but from the boiling liquid. This will be a gas from the boiling liquid. If we are talking about water as our liquid, this is water, then at the lower point where you are directly in touch with the heat, assuming that this is the Bunsen burner, or if you are at home, any burner you are using, this point will be more hot than any other part. So the water that will be at the lower point will boil faster than the water that will be far away from the point that is very hot. So the water that is on this surface will turn from liquid to gas. And being in gas form, and remember gas form but at the lower point of that apparatus that you will be using for boiling of the water. So what do you expect? Being a gas will obviously go up since it is less dense than water. But remember, it is not just one bubble. So many are being produced at the same time. So they will all be being produced at a faster rate. And that's what you see now, the water kind of jumping up and down. It's just the expulsion of the gas that will have been formed. But this gas is not just any other gas, but the gas coming from the liquid that is being boiled. If it is water, it is gas from water. If it is ethanol, it's gas from ethanol. So it will depend on the liquid you are talking about. If it is mercury, maybe you are talking about mercury. Remember you mentioned this is a liquid we commonly interact with in thermometers, which has a melting temperature of -39 degrees centigrade. But at 357 degrees centigrade, 357 degrees centigrade, then mercury will change from liquid to gas. So if you can have a source of energy that can take you to such a temperature, then still you will see whatever I'm mentioning here of air bubbles coming from the bottom as they move up. This process of these air bubbles going up is what we call boiling. This process of these bigger, not small ones, big air bubbles coming out from the bottom of whatever material you are using to boil water is what we call boiling. But this process of water moving up as steam, then later on disappear as into air, is what we call evaporation. Boiling must be done at 100 degrees centigrade at sea level. Evaporation can be done at any temperature. Evaporation is done at any temperature. That is the difference between the two. Now, we have talked so much about the change of state from solid to liquid, liquid to gas, and vice versa. We have seen the two cases where you have water and dry ice. Dry ice undergoing a special process called sublimation, and the other one going through all the processes we have noted. I also mentioned that in the change of state, the substance always remains the same. But there's one point I will wish I clarify, and this is the point of heating candle wax. When you light your candle, it is lighting. I've just said that when you are melting a substance, the melt should be equal to the solid that is giving out the melt. But do you think the amount of melt you get from a candle is equal to the solid part of the candle that you are burning? I'm sure it never happens that way. It's not. Why is it different? How can we be able to explain that? This one takes us to a point to do with the burning. Remember, with this candle burning, it means this flame must be consuming part of this in a particular way. So as much as there is that melt, there is a melt here, but you will not see much of it flowing down. Not much of it will be flowing down. And within maybe an hour or two, you will find now your candle is at this point. What has happened? So you have to remember that there is what we call burning. And burning means something must be consumed. Something must be consumed. This is a chemical change. And a chemical change means substance A must combine with the B so that you form C. A is totally different from B, B different from A, B different from C, A different from C. That's a chemical change. So this candle is a substance we call a hydrocarbon. This is a hydrocarbon, meaning that a compound that contains carbon and hydrogen. A compound that contains hydrogen and carbon, something that we'll understand in more details later, but we can only concentrate on the part we can manage at the moment, and that is know that candle is a substance made of carbon and hydrogen. So if I have carbon and hydrogen and I'm doing the burning in air, the burning is being done in air. So this hydrocarbon is combining with the air, and the air here we are interested in oxygen gas. So because of that, the hydrogen part takes part of oxygen. The carbon part takes part of oxygen to form new substances or compounds. So the hydrogen part takes oxygen to form water. And the carbon part takes oxygen to form carbon dioxide. Carbon dioxide. So as you can see, the compound we had was carbon and hydrogen. But what we are having at the end, it is hydrogen and oxygen, carbon and oxygen. Totally two different substances. This is a chemical change. So part of this candle goes in the air as water vapor and as carbon dioxide. So this explains why the melt you see here is not equal to the amount of candle wax solid that was being burned. So that's, I think, a good clarification, so that in case you will be wondering that earlier on I had said no loss, no gain. So the substances must be equal, but it does not apply to all cases. And an example is melting candle wax. As you can see, if you are melting through burning, then this is what you will see. However, if you melt this candle wax, melting is different from burning. You have candle, put it on, for example, a pan. You have a pan, you have your candle lying on that pan, not yet burning. Then you heat it strongly until it starts melting. Then at this point, the wax will be equal to the melt. Hope now you get the difference. If it is melting through burning, then the melt will not be equal to the wax. If it is melting through heating, then the melt will be equal to the wax. Having done that, you remember in our previous lessons, we mentioned that even if you carry out a very good experiment, but you don't record your data properly, then everything is to waste. So, when you are talking about this process of melting, evaporation, condensation, freezing, sublimation, they can well be presented through graphs. So I want us to look at how you can represent the information I've just talked about on a graph. And we shall start with that of heating ice water. Ice water heated. Ice water heated. You know very well that from ice water we shall go to liquid water, then from liquid water we shall go to steam water or vapor. Those are changes. But we have also quoted particular temperatures, 0 degrees centigrade and 100 degrees centigrade of pure water at sea level. Now, how do you represent these on a graph? A graph has the y-axis, which is this one, and the x-axis. Now, on this one, you have to state the temperature. So, we shall have our temperature on the y-axis, which is in degrees centigrade. Remember, we have two scales, Kelvin scale and Celsius scale. So, we are using the Celsius scale. Then, this other part, we have the reaction path. Reaction path. Now, if we can have this one as 0 degrees centigrade, then we have this point as 100 degrees centigrade. And we are talking about ice. This ice can be at a lower temperature of, let's say, even 10 degrees centigrade, negative 10 degrees centigrade. So we can still extend this one. We know very well, if you haven't understood very well, you should ask your mathematics teacher to elaborate on this, that we have the positive side, then we also have the negative side of this Cartesian plane. So this side is positive, this side is negative, this side is positive, this side is negative. Now if you are talking about negative 10 degrees centigrade, so it can be probably somewhere like at this point, negative 10 degrees centigrade. Remember, this is not plotting, we are sketching. So if you are heating water, you can have water moving from negative as it heads to 0. Once it reaches 0 degrees centigrade, maybe using a different ink, it can give us a clear picture. Now, if you have this water moving from negative, remember we have said negative 10 degrees centigrade, so it is moving from negative, heading to 0 degrees centigrade. At this point of 0 degrees centigrade, which is the melting temperature, as you add in heat energy, remember, for it to melt, you have to add in heat energy. As you add in heat energy, that heat energy will not do what it was doing between negative 10 and 0 degrees centigrade. It will do something else. So first of all, what is it that was happening between negative 10 degrees centigrade, which is at this point, to 0 degrees centigrade? The heat energy you are adding in was just raising the temperature. The heat energy was raising the temperature from negative 10 degrees centigrade to 0 degrees centigrade. But on reaching 0 degrees centigrade, which is a melting point at sea level, a melting point of a substance at sea level, and the substance here is ice water. And remember, the water must be pure. Then the heat energy will do a different purpose, and that is it will start breaking the bonds. It will start making the particles to vibrate more strongly to break off from each other so that they can start rolling over each other. In so doing, it will not be increasing the temperature. It will only be breaking the bonds, that forces that are holding the particles together. It's just like, for example, if you are writing, I doubt by writing if you will be listening properly. You must do one thing at a time. You either listen or you write. So you will find that if you want to do good writing, then you have to concentrate on writing. And if you want to do good listening, then you have to concentrate on listening. So the same happens to this. You either do the rising of the temperature or you either do the breaking of the bonds, just one. So -10 to 0, you are rising the temperature, not breaking the bonds. So you move from -10 to 0 degrees centigrade. At 0, you now do the other one, break the bonds. Because of that, the temperature will be constant. Maybe let me remove this one so that we use red here to show that at that point you are breaking the bonds. What is happening? Melting is taking place. On completing all the ice moving to liquid water, you have now done the melting of everything. Then addition of heat energy will no longer be doing the breaking of the bonds, but it will now be doing the rising of the temperature. Rising of the temperature. On reaching 100 degrees centigrade, the same happens whatever happened down here. That is, you do again one thing at a time, and that is break the bonds from liquid to now gas. So because of that, the temperature will not be rising, it again remains constant. So here we shall be talking about boiling, not evaporation, boiling, because we are quoting 100 degrees centigrade. And here we shall be doing melting of a pure substance. It is sharp and it is also sharp. This is what we call heating curve of water ice. And you can as well do cooling curve of water ice, such that if this water was now in gas form, if you do condensation at 100 degrees centigrade, then condensation will be done. That is when you are cooling. As you continue cooling, the temperature will continue dropping. On reaching 0 degrees centigrade, it will be constant. Why? Because freezing will be taking place. So here you will be talking about condensation, and here you will be talking about freezing if it is a cooling curve. And if it is a heating curve, then you talk about melting and boiling. Now, as an assignment, I will leave you with draw a heating and cooling curve of heating dry ice. You draw a heating and cooling curve of dry ice, just like what you have done. Remember, it undergoes sublimation. That marks the end of our lesson today. Till next time, thank you.